Good afternoon, everyone. So, welcome to the continuation of the lecture series on instabilities, waves, and mixing in stratified flows. This lecture series is being held under the SPARC program with the speakers as listed in the slide here. Thierry Doxois, Sylvain Jobo, and Philippe Odier from ENS Lyon, and myself, Manikandan Mathur, and Anubhav Roy at IIT Madras. Just a second. So this is the first lecture of day 2. Anubhav Roy gave a very nice set of 2 lectures yesterday, going from discrete systems to one-dimensional continuous systems to 2 and 3D continuous systems, and finally talking about fluid flows and waves in fluids in general. Okay, so we are going to build on those lectures. And the main change from yesterday's content is going to be that we are now going to consider a continuously varying density stratification in the background field and see what kind of waves such as a background state can support. Okay, so more specifically, I'm going to be talking about internal gravity waves, and we are going to continue in the linear regime. So in line with the approximations that Anubhav made yesterday, saying the perturbations that you're adding to the background state are small. And as we go along in the week, you will see aspects on nonlinear internal waves in various lectures, specifically in Thierry Doxois lectures, one of which is focusing on nonlinear internal waves. Okay. Like yesterday, Ramana, can you confirm that you are able to hear me and see my screen?
Yes, sir. I can hear and see the screen.
Thank you.
Oh.
Okay, so let's get started. And as Anubhav pointed out clearly, this is targeted towards an audience which has some fluid mechanics background, but as such, we are assuming that they are either getting started in this field. So it's going to be pedagogical in nature, talking about the very basics of the foundations of internal gravity waves. Okay, so let's get started. I would like to start with a simple argument talking about what represents the restoring forces in internal gravity waves. And then I'll switch over to my tablet or a whiteboard where we will try and derive the dispersion relation for internal gravity waves. Okay, so what we're going to consider is a background state where you have the density varying with depth. Okay, so as indicated in this picture, you have heavier fluid at density ρ2 at the bottom of, let's say this is a tank, and a lighter fluid ρ1 at the top. Let's further assume that it's a linear variation of density with depth. Further, there is no flow in the background, so this is quiescent fluid and is stably stratified. It's stably stratified, as you have seen for the discrete or a sharp interface limit. When you have a heavier fluid sitting below lighter fluid with no background flow, it is a stable scenario. So similarly, one can also show that when it's continuously varying density profile, with density always increasing with depth, it is a stable stratification. So what I want to consider to begin with is a fluid parcel at its equilibrium location. So let's say it's at a depth where the surrounding density and the fluid parcel's density itself is ρ0, and it experiences its own weight in the downward direction. ρ0 is the density of the parcel itself, the capital V is the volume, and I'm assuming gravity to act along the negative Z direction or downwards in this picture. Right, so this fluid parcel is in equilibrium because of the hydrostatic pressure distribution. It also experiences a buoyancy force, And if you think of buoyancy force as the weight associated with the volume of fluid that the fluid parcel has displaced, it would also be the same as the weight of the parcel itself. So balance between these two forces means in the absence of any perturbations, this fluid parcel is in equilibrium and will be happy to continue remaining so forever if there are no perturbations. And let's think of a scenario where we take this fluid parcel and displace it by a height z. And as indicated here, let's say it's displaced in the upward z direction. What would happen now? There is no diffusion, okay, and it's an incompressible flow. So the fluid parcel's density continues to be its original density rho naught, and so it continues to experience its own weight, which is the same as what it was in its equilibrium position, which is rho naught v times g. But now the buoyancy force would have changed because the density of the surrounding medium has changed. More specifically, in this stable stratification, the density of the surrounding medium has reduced. So now you have the buoyancy force being given by not just rho naught times Vg, but a small change in the surrounding density given by d rho by dz multiplied by the displacement z itself. And d rho by dz here being negative, the buoyancy force is now going to be smaller, which means the net force is now going to be restoring or downwards because weight is the same as what it was originally. Right, so one can write down a simple equation of motion for this fluid parcel. The first term z double dot here is its acceleration, and the second term that you see here is a result of the net force that you would write down on the right hand side. I've brought it to the left hand side. The net force is essentially the difference between W and B at its displaced location. So this is a simple spring mass type equation. If you write down this entire factor minus g by rho naught into d rho by dz, given d rho by dz is negative because it's stably stratified, minus g by rho naught into d rho by dz is going to be a positive quantity, and I'm going to denote it by n square. Okay, so the equation of motion for this fluid parcel is z double dot plus n square z is 0. And if you look at the dimensions of this quantity, n square has the dimensions of a square of a frequency. So n itself is what has come to be known as the buoyancy frequency. It also sometimes referred to as the Brunt-Väisälä frequency. Okay, so this represents the natural frequency of oscillations if you displace a fluid parcel in the vertical direction in a stably stratified medium. So the natural frequency depends only on the magnitude of the density gradient. Okay, so that's important to note. The stronger the density gradient, larger is going to be the free buoyancy or the Brunt-Väisälä frequency value. G is the acceleration due to gravity, is going to be assumed constant throughout my couple of lectures. And rho naught in the denominator here is a reference density. Okay, so like yesterday, if there are any questions, please do interrupt. And Ramana, requesting you that if I have not seen a question and you do let me know that there has been a question.
Sure.
Thank you. Okay, so now the next question asks, okay, there is a natural frequency that is present if you displace the fluid parcel vertically. Now I can also ask, hey, why displace it vertically? Let me think of a scenario in which the frequency of oscillations of this particle is some other frequency omega, and that is smaller than this Brunt-Väisälä or the natural frequency n. Okay, so I will say, okay, by some means there is a frequency omega, so the vertical displacement of this fluid parcel is going to be written as an amplitude times sine omega t. What would happen in that scenario? I substitute in the governing equation that we have written down for vertical oscillations of the fluid parcel. Now you're going to have minus omega square a plus n square a is 0, but we have intentionally chosen the frequency to be smaller than this Brunt-Väisälä frequency, and so the equation of motion will not be satisfied. So this is suggesting that if the frequency is omega, then it may not be viable for us to think of purely vertical oscillations for this fluid parcel. So given the restoring force is now too strong, if omega is smaller than n, naturally I think of, hey, what if the direction of motion for this fluid parcel is not entirely vertical, but at some orientation with respect to the vertical. That would mean that the change in the buoyancy force would be modified. And so this excess restoring force that you are getting may be compensated for, right? Or if it's oscillating at an angle with respect to the vertical, then the reduction in the buoyancy force may not be as drastic as if it was oscillating vertically. And that may be a means by which you can support the frequencies that are smaller than the Brunt-Weisel frequency. Indeed, if you consider oscillations with the direction of motion for the particle being along an eta direction that is as indicated, you can write down the equation of motion along eta with the angle theta being given by the direction of motion and the horizontal. And then you can again write down for as a governing equation for eta, again a spring mass type equation, now with the frequency being given by n sine theta. Because please recall what appears as this coefficient is a square of a frequency. So now you can have, if omega square is given by n square sine square theta, or I'm just taking a square root, not worrying about the signs or plus or minus possibilities, I finally write down that sine theta equals omega by n. So what I'm figuring out with these simple arguments is that if the fluid parcel is going to oscillate at an angle theta with respect to the horizontal, then it could potentially have frequencies that are smaller than n, and the relation between the frequency of oscillations omega, the Brunt-Weisel frequency n, and the angle of motion of these fluid parcels is related by sine theta equals omega by n. Okay, it turns out this represents the dispersion relation. Again, it is kind of a coincidence that we have been able to recover the dispersion relation through these very simple arguments. In reality, you don't have isolated fluid parcels moving around. This is a continuous fluid. So the motion of one fluid parcel influences what happens around it, or influences the motion of fluid parcels around it. So we have to more rigorously consider a velocity field or a flow field where all the parcels are moving at the same time, and see what the dispersion relation comes out to be. Okay, so what I'm going to do is, having obtained this intuitive understanding and recognizing that buoyancy provides a mode for restoring force. So clearly, oscillations are possible for individual fluid parcel trajectories. Now, can this restoring force provide a means for supporting waves? And what would the waves look like? What is the dispersion relation for those waves? And I'm kind of giving you the final result already, that sine theta equals omega by n that we obtain with very simple arguments will turn out to be the actual dispersion relation that relates the temporal frequency and the spatial wave vector for perturbations. So if there are no questions at this point, I will switch over to my tablet and try and, like in a classroom scenario, try to derive the dispersion relation more formally. Like Anubhav did, we will consider a background state, add perturbations to it, and linearize the governing equations to then look for plane wave solutions to finally obtain the dispersion relation. All right. So give me a moment to switch over to my tablet and I will share screen from there. Okay, so we are going to take up this task of deriving the dispersion relation for internal waves. Okay, so let me define the coordinate system first. I'm going to restrict myself to 2D at the moment. I will mention 3D dynamics probably later in this lecture or in my next lecture. So we will define horizontal x and vertical coordinate z with gravity acting along negative z. Okay, and we are going to also assume incompressible flow dynamics, which essentially means that the material time derivative of the overall net density of fluid parcel is going to be 0. So the first task in any of these calculations is to define the background or the base flow state. Let's do that now. So the background or the base state is going to be given by is going to be denoted with a subscript b and has velocity components little ub and little wb, right, along x and z respectively, and this is going to be 0 because we are considering quiescent flow. All right. We have to define the background density field. So that I will denote as rho b. And let's, given what I've assumed in my slide, so this is going to be given by some vertical profile rho bar as a function of z alone. So there is no functional dependence for the background density field with either with respect to x or t. So this is a stably stratified density profile. And specifically, if rho bar of z is linear, then that's what is referred to as a uniform stratification, because the density gradient, which is what the Brent-Weissela frequency depends on, is going to be constant if rho bar of z is linear. Okay, so right now I will not even assume rho bar of z to be linear. It's just some stably stratified density profile. Okay, and finally we need what the pressure distribution associated with the background state is, and I'm simply going to write this is given by the hydrostatic pressure distribution, which you will obtain by writing down dpb by dz, or yeah, so that should be equal to minus rho b into g. Please stop me if there are any questions. Okay, so having defined the background state, now we can consider small perturbations on the background state to see what the linearized governing equations of the perturbations is going to be. So I'm going to write down the net flow field U as equal to UB plus U prime, and given UB is uniformly 0, this would be just U prime. And we can denote this by its components along x and z as little u prime and little w prime. Similarly, we are going to take the net density field as being given by, in general, the background density rho b plus a perturbation field rho prime. Okay, let me also highlight here that this perturbation in general, u prime, is going to be a function of the spatial coordinates x and z and time t. Similarly, w prime is also going to be a function of x, z, and t. Okay, so the net density is going to be given by rho bar of z plus rho prime being given by pb plus p prime of x, z, and t. So this is my background state plus perturbations. And at this point, we have not made any assumptions about the amplitude of the perturbations. This kind of decomposition can be done for any flow field. And as we go along, when we write down the governing equations for the perturbation fields, we will make the small amplitude approximation. So now let's write down the governing equations, which the background state and the perturbation field and the net flow field will have to satisfy. So governing equations. The background state has to satisfy the governing equations because the background state represents an equilibrium state. And the net flow field, any evolution of perturbations has to follow the governing equations for the net flow field. So the governing equations, we're going to start by writing down mass conservation. And the mass conservation equation is for an incompressible flow is given by simply the divergence of the net velocity field being equal to 0. So I'm going to write down that this is the mass conservation written down for an incompressible flow, right? And given UB, the background UB is 0, this also means the divergence of the perturbation velocity field has to be equal to 0, implies U prime can be represented in terms of a stream function. That's because we are also operating in 2 dimensions in terms of a stream function. So I'll write down, recall, we are in 2D. All right, so I'm going to define this stream function that represents the perturbation flow field. So I'm going to write down little u prime as equal to dou psi divided by dou z, and little w prime as equal to minus dou psi divided by dou x, where psi in general is a function of x, z, and t, is the perturbation stream function. Right. So given we are representing the flow field in terms of a stream function, we don't even have to worry about explicitly satisfying the mass conservation equation anymore, because by definition, a flow field described by a stream function would be divergence free. Okay, so this implies u prime equal to 0 is satisfied. That's great. And we have also reduced the number of variables from the 2 components of velocity to a single scalar field, which is the stream function. So then what I'm going to do next is to write down the momentum equation. Right, which in general is going to be given by the net density rho multiplied by the material time derivative of the velocity field, which let me write as dou u by dou t plus u dot grad of u is going to be equal to minus grad p plus viscous terms, which I'm going to ignore for this lecture, Again, I may mention the effects of the viscous terms a little later on in the lecture or in the next lecture, plus the external force due to gravity, which I'll write as the net density times the gravity. Okay, so I'm going to write down the fact that we are making this inviscid approximation. So now let's break this down into the x and the z components. So if I write down the x component, we're going to have rho multiplied by dou u prime by dou t plus u prime dou u prime by dou x plus w prime dou u prime by dou z, and this in general would be equal to minus dou by dou x of the net pressure. So I'll write this down as minus dou pb by dou x minus dou p prime by dou x. So I'm just writing p as pb plus p prime. Again, the net density, I'm going to write down, this is the x component, gravity being along the negative z, there's going to be no contribution from the gravity term to the x momentum equation. Okay, so I'll write down here that g is given by minus g ez hat. All right, so let's take care of some of the easier terms that we can ignore here. Dou pb by dou x is 0. It's because we are considering a background state in which the pressure distribution is hydrostatic and hence dependent only on the z coordinate. So dou pb by dou x is 0. I'm going to ignore u prime dou u prime by dou x because both u prime and dou u prime by dou x are perturbation quantities. So we're making the small perturbation approximation at this stage. So I'll just say ignore, the justification being we are considering small perturbations. So this is the part of the linearization. Similarly, w prime dou u prime by dou z should also be ignored due to the same reason. So I'll write ignore. If you recall from yesterday's lectures of Anubhav, he considered a background shear flow. So then there were some terms that couldn't be ignored, that coming from the convective derivative. But here, since our background flow is 0, this u dot grad u is going to be always nonlinear or small. Okay, so it is possible that you can consider internal waves in the presence of a background flow, but that's not a scenario that I'm going to consider today. All right, and finally, we have the density rho that appears here, and I am going to replace, so strictly speaking, this rho has to be equal to rho bar plus rho prime. All right, one can ignore rho prime into dou u prime by dou t because of linearization. So ignore rho prime into dou u prime by dou t. Right, that's also because of linearization. And in addition, I'm going to replace the rho bar with a reference density rho naught. Okay, so this is more generally known as the Boussinesq approximation, where density variations are important to retain only in the external gravity force. Okay, so the density variations in any other terms, like it appears here as the coefficient in the inertial terms on the left hand side, one can replace the overall density, even though rho bar is strictly speaking a function of z. The variations are sufficiently small over the entire depth that I'm able to replace that rho bar with constant reference density rho naught. It turns out the primary dynamics that we want to focus on will not be lost because we are still going to retain density variations in the gravity term on the right hand side. in the Z momentum equation. Okay, and we know from our intuitive arguments in the first slide that retaining density variations in the buoyancy force is what is critical in representing the restoring force or the underlying physical mechanism for wave propagation. But the density variation that's present in this on this inertial term on the left hand side, I'm going to replace with a reference density rho naught. There are a few different justifications you can give for this approximation to be reasonable. The simplest being, if you take either the ocean or the atmosphere, the overall changes in the density rho bar, for example, in the ocean, the overall change in the density over an entire depth of around 4 kilometers will be of the order of 10 kilograms per meter cube. Right? So you're talking about the density going from, let's say, fully fresh water at the ocean surface, and that value around 1000 kg per meter cube. And the density at the bottom of the ocean could be of the order of 1010 kg per meter cube. That's just a ballpark estimate. But the main idea being the overall density variation itself, it's 10 out of 1000. So that's like 1% variation. So it's not so critical to retain in this term on the left-hand side. But still, even that 1% variation is what is critical in providing the restoring force. So it is important to retain the density variations in the buoyancy or the gravity term. So replace rho bar with the reference density rho naught, and I'm going to refer to this as the Boussinesq approximation, which in general can be stated as retaining density variations only in the gravity term and replacing density variations with a constant reference density in the density that appears on the left hand side. Okay, so if we and this is this Boussinesq approximation is distinct from the linearization we have done. Linearization concerns ignoring terms that involve products between perturbation quantities, but here we are ignoring the small changes that are present in rho bar of Z itself. Okay. Okay, so if you allow me to make that approximation, we are going to finally have rho naught into dou u prime by dou t, and on the right hand side is simply going to be minus dou p prime by dou x. So let me call this as equation 1, which is the linearized form of the x momentum equation. One has to do the same on the z momentum equation. So let's take that up now. Okay, so the z momentum equation in general is going to be the net density rho times dou w prime by dou t plus u prime dou w prime by dou x plus w prime dou w prime by dou z, right, is going to be equal to minus dou p divided by dou z. I'm writing down, yeah, the net flow field quantities, but the velocity field we know, since the background flow is quiescent, I've just replaced the velocity terms with the perturbation w prime and u prime. But still on the right hand side, it's the net pressure P plus the external force due to gravity, which I'm going to write as rho bar of Z plus rho prime acting along the G vector. So this is can be written as minus G because this is along the EZ axis. So let me write this as equal to minus dou PB by dou Z minus dou P prime by dou Z minus rho bar of Z into G minus rho prime into G. Now we are going to make use of the fact that the background state also satisfies the governing equations. In other words, the background pressure distribution is hydrostatic. So these two terms will combine to give 0. hydrostatic pressure distribution in the background. And so we have dPb divided by dz being given by minus rho bar of z into g. We have written this down already. So the right hand side is going to simplify to minus dou p prime divided by dou z minus rho prime into g. Okay, on the left hand side, we can ignore these two terms due to linearization, or assuming that the perturbations are small. So I'm going to write down linearize. And like we did for the x momentum equation, we will first write down rho as equal to rho bar plus rho prime. Rho prime into dou w prime by dou t is to be ignored because of linearization, and you're going to replace rho bar with constant reference density rho naught. So finally, the z momentum equation is going to simplify to rho naught into dou w prime by dou t. Is that right? Yeah. Is equal to minus dou p prime by dou z minus rho prime into g. Let's call this as equation number 2. All right, and one can also write this equation number 1 in terms of the stream function, right? We have already decided to express u prime and w prime in terms of a stream function. So I can write this as rho naught. I think u prime was dou psi by dou z. So this would become dou square psi divided by dou z dou t is equal to minus dou p prime divided by dou x. So let's call this as 1 star. You've essentially written u prime in terms of the stream function and going from 1 to 1 star. Similarly, going from 2 to 2 star, w prime is minus dou psi by dou x. So this would become rho naught into dou square psi divided by dou x dou t is equal to dou p prime by dou z plus rho prime into g. So this is going to be my 2 star. So let me try and combine 1 and 2, 1 star and 2 star. My aim here is to derive a wave equation for internal gravity waves. And I'm trying to express the final wave equation in terms of a single variable. I'm going to choose that to be the stream function psi. One can express the final equation in terms of other variables too. But in this lecture, let me make the choice of trying to eliminate all the other variables and retain only psi. So if I can look at 1 star and 2 star and look to eliminate pressure by differentiating 1 star with respect to z, right? So dou by dou z of 1 star, and that's going to give me minus dou square p prime by dou x dou z. And you add this with dou by dou x of 2 star. So this is going to give me, you're differentiating 1 star with respect to z. So rho naught into dou square psi by rho naught into dou cube psi by with respect to dou z square dou t. Right? And the left hand side from 2 star, we are going to differentiate that with respect to x and add so that the pressure term gets cancelled. So we're going to have rho naught into dou cube psi divided by dou x square dou t. On the right hand side, the pressure will not be there. So we are simply going to have g multiplied by dou rho prime divided by dou x. Yes, and the pressure term is eliminated. Is that okay? So we now have a simplified equation which is written almost entirely in terms of the stream function, perturbation stream function psi, but you still have the density perturbation appearing on the right hand side. So we need an additional constraint that would relate the stream function and the density perturbation, and that comes from the statement of incompressibility. Right, for those of you familiar with compressible flows, this statement of incompressibility is going to play the role of the equation of state. So the statement of incompressibility in our flow is simply that d by dt of the net density rho is equal to 0. Recall that we have already made use of this statement in simplifying the mass conservation equation, but we have still not explicitly written down the material time derivative of rho being equal to 0. So that's going to say you have dou rho by dou t plus u prime dou rho divided by, am I getting this right? By dou x plus w prime dou rho by dou z is equal to 0. Right, and let's now decompose rho also into a background plus a perturbation. So you have dou by dou t of rho bar plus rho prime plus u prime into dou by dou x of rho bar plus rho prime plus w prime into dou by dou z of rho bar plus rho prime is equal to 0. Now dou rho bar by dou t is 0 because rho bar is a function of z only. So you're going to have dou rho prime by dou t plus u prime into dou rho bar by dou x, but dou rho bar by dou x is 0 because rho bar is a function of z only. And the second term is going to be u prime dou rho prime by dou x, which is ignored now owing to linearization because it's a product between perturbation quantities. So both the terms of the second term is going to be 0. From the third term, you're going to have plus w prime into dou rho bar by dou z, which I will write down as w prime into d rho bar by dz. And the final term is going to be a product between w prime and dou rho prime by dou z, product between perturbations. So I can ignore that as well. So this is equal to 0. So let me write down rho bar is rho bar of z and comma, you also linearize. All right, and written in terms of the stream function, this is going to be dou rho prime by dou t plus w prime is going to have a negative sign when written in terms of the stream function. So you're going to have minus dou psi divided by dou x into d rho bar divided by dz is equal to 0. Let's call this as equation 3. Maybe let's call this as our equation 3, and this would be the linearized equation resulting from incompressibility is equation 4. So what are we trying to do? Eliminate the density perturbation that appeared in equation 3. So you have dou rho prime by dou x. So and we have dou rho prime by dou t appear here. So let's differentiate 3 with respect to t. So dou by dou t of equation 3, which is going to give us dou square rho prime by dou x dou t. And let's differentiate 4 with respect to x. So we're going to do plus g into dou by dou x of 4. Right, so dou by dou t of equation 3, let's see what it gives us. It's going to give us rho naught into dou square by dou t square, rho naught into dou square by dou t square of dou square psi by dou x square plus dou square psi by dou z square. That would be the first two terms. On the right hand side, we are differentiating with respect to t. So you're going to have g times dou square rho prime by dou x dou t. So this is going to be equal to g into dou square rho prime by dou x dou t. Is that correct? Yeah. And we are differentiating 4 with respect to x. So we will have on the left hand side plus dou square rho prime divided by dou x dou t. We're also multiplying it with g. And the second term is going to be minus g into dou square psi by dou x square into d rho bar by dz. Because rho bar is a function of z only, differentiating the left hand side, the second term on the left hand side of equation 4 is only going to give us dou square psi by dou x square into d rho bar by dz. Okay, as expected, this is what we are trying to do. This gets cancelled, and so we finally have dou square by dou t square of dou square psi by dou x square plus dou square psi by dou z square minus g divided by rho naught into d rho bar by dz into dou square psi by dou x square is equal to 0. Is that fine? Now let's recall from the first slide that minus g by rho naught into d rho bar by dz. Yeah, that was for a linear density profile. We said that's n square. But now, even if rho bar is a nonlinear function of z, you can think of minus g by rho naught into d rho bar by dz as some n square. Now the difference being, if rho bar is a nonlinear function of z, n square in general is going to be a function of z. So n square of z is minus g divided by rho naught into d rho bar by dz. So it's indeed quite nice that the Brunt-Väisälä frequency, the buoyancy frequency, is naturally turning up in the wave equation. So the final internal wave equation right? We have made several assumptions. Let's recall. First, the viscous terms have been ignored. So this is inviscid limit. We have made the Boussinesq approximation. We have assumed that the perturbations are small. So combining all the, and we are operating in 2 dimensions. So combining all these, the final internal wave equation can be written down as dou square by dou t square into dou square psi by dou x square plus dou square psi by dou z square plus n square, now with the definition for n square being given above, into dou square psi divided by dou x square is equal to 0. So let me write down all the approximations. Inviscid, Boussinesq, we are operating in 2D. It's incompressible. And most importantly, we're considering small perturbations. So I'll write down linear, or in other words, small perturbations. The idea of doing this derivation live is that now one should be able to think about what happens if you choose to retain the nonlinear terms as well, because you're going to get additional, more complicated terms that will lead to dynamics that are richer than simply linear wave dynamics. But my aim in this lecture is to just tell you about the linear wave dynamics, which is for internal gravity waves is already sufficiently rich and interesting. Okay, so we have managed to derive the internal wave equation, and we have to proceed towards deriving the dispersion relation. At this point, if there are any questions, I'm happy to take. If not, I will proceed to derive the dispersion relation. Okay, so I assume there are no questions at this point. So if we want to derive the dispersion relation, let's recognize that we'll derive the dispersion relation for the limit of n square being constant. So I would like to, because we look at the internal wave equation, the problem is homogeneous in time and the horizontal coordinate x. Okay, because both in time and x, it's infinite in extent, and there are no coefficients that explicitly depend on time or x. But since I've said rho bar is an arbitrary function of z, it is potentially possible that n square here is a function of z that breaks the homogeneity in the z direction. That would not allow us to look for plane wave like or exponential variation along the z direction. So to keep the homogeneity in z also, I will say assume n square of z, which as equal to some constant n naught square, and this is what is often referred to as uniform stratification. Okay, so if one is thinking of the ocean or the atmosphere, you would imagine that you're still capturing some leading order dynamics by assuming uniform stratification. Surely we are doing much more than assuming uniform density, because we know accounting for even a linear variation of density is going to bring in the restoring buoyancy forces, and so the basic mechanism for wave propagation is retained. And I will talk about non-uniform stratification effects in my next lecture. Okay, so if you assume this, the problem is homogeneous in X. So this would imply the problem is going to be homogeneous in X, Z, and T, which okay, I saw a question pop up. I will, let me come back to that question. Let me just derive the dispersion relation. All right. So the homogeneous in X, Z, and T. So I am going to look for plane wave solutions, or in other words, going to look for psi as being equal to some constant amplitude into an exponential of I multiplied by kx into x. So there's a horizontal wave number kx, vertical wave number kz, and frequency in time omega. All right. Like Anubhav discussed yesterday, let's consider temporal stability analysis. So you're going to consider real wave numbers. So if we do temporal stability, would mean you're going to consider real kx comma kz. And this also makes sense because we have the spatial domain being infinite in extent along x and z, going from minus infinity to plus infinity. So an imaginary, non-zero imaginary part for kx and kz would mean this kind of a plane wave would diverge either at minus infinity or plus infinity, even at initial time. So that would be unphysical. So that's also a reasoning or a justification we would give for assuming real wave numbers. Okay, so the wave vector itself, now we are operating in 2 dimensions. So the wave vector is thought of as the horizontal wave number kx along ex plus the vertical wave number kz along ez. Are there any questions? Okay, so I will get to that question in the chat box in a little bit of time. Okay, so the wave vector is kx, ex plus kz, ez. I'm assuming this is a plane wave, or this can also be thought of as the normal mode that Anubhav was discussing yesterday. So let me write down this as a plane wave. Okay, and what does the dispersion relation generally give us? Substituting this plane wave form in the governing wave equation is going to give you a relation between the spatial wave vector kx comma kz and the temporal frequency omega, which is exactly what the dispersion relation is. So let's go ahead and do that to the internal wave equation we have derived. You have dou square by dou t square. Dou square by dou t square is going to give you minus omega square multiplied by dou square psi by dou x square is going to give us minus kx square. Dou square psi by dou z square is going to give us minus kz square plus n square into dou square psi by dou x square, and dou square psi by dou x square would be will give us minus kx square. This is equal to 0. So we finally have kx square divided by kx square plus kz square is equal to omega square divided by n square. This is the internal wave dispersion relation. Right? There are several interesting properties contained in here, but let's absorb what we have here. On the left hand side is terms containing the wave vector components kx and kz. But as you notice, the left hand side does not depend on the actual magnitude of the wave vector itself. It's a ratio between kx square and kx square plus kz square. So this is as some relation to the orientation of the wave vector. And on the right hand side, there is dependence on the frequency of the perturbations omega. And let me explicitly point out that we have assumed the stratification to be uniform or the density profile to be linear. So I will replace the n with n naught. So if I think of the wave vector k as making an angle theta with the z-axis, right? Then kx square divided by kx square plus kz square can be interpreted as sine square theta. Right? So the dispersion relation essentially tells us that the sine square of the angle that the wave vector makes with the z-axis should be equal to the ratio between the frequency of the internal wave, square of the frequency of the internal wave, and the square of the Brunt-Väisälä frequency. Let's recall that the Brunt-Väisälä frequency is a frequency, is somewhat like a natural frequency associated with the strength of the background density gradient. So let's just recall that n naught square is equal to minus g divided by rho naught into d rho bar by dz. All right, so this is interesting now because it gives a relation between not the frequency and the wave vector components, but this gives a relation between the frequency and the wave vector orientation. Right, and what would be the phase velocity? So Anubhav introduced the concept of phase velocity yesterday. He had done that for a 1D wave system. And he also pointed out that in general, the phase velocity is going to be along the wave vector itself. So let me define the phase velocity as equal to omega divided by the magnitude of the wave vector, with the direction being along the wave vector itself. So I will write that down as k hat, which is the unit vector along the wave vector. So this is just k divided by mod k. All right, so for our problem, this is going to be equal to omega divided by square root of mod k is square root of kx square plus kz square, and multiplied by kx ex plus kz ez. And this is a unit vector that we require along the wave vector k. So this has to be again divided by square root of kx square plus kz square. So this would be simply omega divided by kx square plus kz square into kx ex plus kz ez. So this is the phase velocity associated with these plane internal waves that we are considering. I am interested in knowing what the group velocity is also. So one can extend the 1D definition for the group velocity that Anubhav introduced yesterday. So now you can think about the direction and the speed with which the wave envelopes will move in 2 dimensions. I'm not going to go into the derivation of the same. I have a couple of slides prepared on this group velocity, but let me just give you the definition as essentially the x component of the group velocity being dou omega by dou kx, and the z component being dou omega by dou kz. Okay, and how do we get dou omega by dou kx and dou omega by dou kz? We have the dispersion relation that we have derived. So omega, kx, and kz are related to each other. So let's write that down in a functional form. We have omega square divided by n naught square as being given by kx square divided by kx square plus kz square. So one can write down 2 omega dou omega by dou kx divided by n naught square is going to be equal to, so differentiating this with respect to x will give me 2kx divided by kx square plus kz square. And if I want to differentiate this kx appearing in the denominator as well, so this will give me minus kx square divided by kx square plus kz square the whole square into differentiating with respect to x, so you're going to have 2 times kx. Right, so this is going to be, if I write down kx square plus kz square the whole square in the denominator, we have 2kx into kx square plus kz square and minus kx square. So this would simply be equal to 2kx into kz square divided by kx square plus kz square the whole square. This is my 2 omega by n naught square into dou omega by dou kx. Similarly, dou omega by dou kz would be given by 2 omega by n naught square into dou omega by dou kz is going to be given by minus kx square divided by kx square plus kz square the whole square. Right, so we are differentiating with respect to z, so we'll have in multiplied by 2 times kz. So finally we have the group velocity being, the components are dou omega by dou kx, dou omega by dou kx, dou omega by dou kz, and that is going to be given by n naught square divided by 2 omega and dou omega by dou kx. So we have a kx 2 kx kz divided by kx square plus kz square the whole square. This is all common. Into, for dou omega by dou kx we have left kz, comma, for dou omega by dou z we have a minus kx. All right, so this is my group velocity. And the phase velocity, let's recall, is given by omega divided by kx square plus kz square. Yeah, omega by kx square plus kz square into kx comma kz. So we now have all the results to bring out one of the most interesting results associated with the internal wave dispersion relation, which is that the dot product between the phase velocity and the group velocity is going to be equal to 0. Right? So tells us that the phase and the energy or the group, the wave envelope, propagate not only with different speeds, which is possible in other wave systems, But here we have a scenario in which they are propagating in orthogonal directions. So phase velocity is orthogonal to the group velocity. Okay, we will see its implications for those of you who are seeing this for the first time. No worries, this is an interesting result, and I have some videos prepared from lab experiments that will tell us what actually this means and what its implications are. Okay, so this is where I want to finish my the tablet writing and switch back to my presentation. But before doing that, if there are any questions in this derivation, I'm happy to take them now. I will take a couple of minutes break to switch over to my presentation, and then I will take the questions that is there in the chat box. Are there any other questions with respect to this derivation? And so in the presentation, I have written down this dispersion relation as a final result, and then I will discuss the consequences or the implications of this internal wave dispersion relation. All right. So give me a couple
Sorry,
of
hi
yeah.
Bunny. Is there a specific reason that you have considered just 2D configuration?
Is there a specific reason why?
That you have considered 2D configuration.
It's simpler.
Okay.
Uh,
So
this
for,
this relation of the phase velocity and the group velocity being orthogonal to each other holds in 3D as well.
okay, okay.
Just
Because
that,
this stream.
yeah, a representation of the flow field in terms of a stream function would not have been possible.
Correct, correct, correct.
And the algebra will be more complex, but by all means, yes, all this can be done in 3D. And this dispersion relation that gives the relation between the orientation of the wave vector theta and the ratio between omega and n naught, this also would hold in 3D.
Okay, okay.
Okay, and very worthwhile and interesting to attempt as well if you are further interested in the subject.
Sure.
Okay, so there was another question specific to this plane wave form. Why don't I just switch over to my laptop presentation and then take the questions. Okay, so give me a couple of minutes. Okay, so let me look at the chat box. There are a couple of questions. Okay, so the first question from Raja was how to think it as a wave equation in 1D. We have second order in time and space here. Yes, so the first point is it doesn't make sense to talk about internal waves in 1D because by definition you have the gravity direction z and the minimum one horizontal coordinate that we have to retain. So this is at the minimum 2D or more because we're talking about these interfaces that span in the horizontal direction. Okay, and then another response I can give is that the internal wave equation still contains the second derivative with respect to time and the second derivative with respect to space. So in that sense, it's terms that are similar to your classical, let's say the acoustic wave equation. Those are the acoustic wave equation is non-dispersive. You have dou square, let's say the pressure perturbation by dou t square as the square of the wave speed times dou square or del square of the pressure perturbation. So you have a similar second derivative terms, but now we are talking about a dispersive system where the phase speed or the phase velocity is not the same for different wave vectors. And that's all I'm able to say right now. So we do have terms that are similar to what you have in the classical wave equation. Of course, it's possible to classify or categorize this PDE in mathematical terms. That's not going to give you additional physical insight. Okay, but standard ideas like following ray paths, following wave vectors are all possible for these internal gravity waves as well. So the second question from Yashodhan says, will the plane wave solution in the z direction work in the case of non-uniform stratification? Very good question. So when you have n square, n not being uniform, not being constant with z, but if n is a function of z, our ansatz where we looked for an exponential dependence on z. We said there is a wave number kz along z is going to break down. So you still can have propagation in the z direction, but that cannot be described in terms of a single wave number kz. Okay. I hope that answers the question. And
Ramana, has the video paused?
Yes, sir.
Can you pause the recording and the streaming?
Okay.
We'll just
Okay.
check to see money might have just dropped.
Okay.
Yeah.
apologies, my internet got disconnected. Let me share my screen. Ramana, can you confirm that you are able to hear and see my screen?
Yes, sir. Yes.
Thank you. Okay, so I pointed out in the first slide that yeah, this relation of sine theta equals omega by n is actually the dispersion relation itself. And now that comment makes sense because it's exactly what we have derived. With a small difference, what the dispersion relation gave us is that sine square theta is omega square by n square. But we had the interpretation of theta earlier as the direction, the angle that the particle displacement makes with the horizontal axis. But now with the derivation of the dispersion relation, theta has the interpretation of the angle between the wave vector and the z-axis. Okay, so that which also tells you that the wave vector direction and the particle displacement direction are orthogonal to each other for these plane internal waves. I will talk to you a little more about it in the upcoming slide. Okay, so what are internal waves? These are propagating disturbances when you have the background state being described by stable stratification, which I took in my notation, I took it as rho bar of z. And we have derived this internal wave equation. This is also written in terms of the stream function. So this is exactly the same equation that we had derived, where the Brunt-Väisälä frequency n is dependent only on the strength of the background density gradient. Okay, so this is related to what Anubhav already presented yesterday. So let me go over this a little quickly. A second interpretation of the group velocity is that if you consider this slide has everything in one dimension. So in general, a plane wave in 1D is thought of as an amplitude times cos of kx minus omega t. K is the wave number along x, and omega is the frequency in time. And the phase speed here can be interpreted as the speed with which one would have to move if you have to remain at constant phase, or let's say you have to remain on a peak or a trough. So the phase velocity is easily defined as omega by k along the x-axis, because this is in 1D anyway. A useful interpretation of group velocity is obtained when you consider the superposition of two different plane waves. Right. So I'm going to here considering the summation of two different plane waves, one at a wave number k minus delta k. Okay. Of course, the corresponding frequency is now modified because the omega and k are related by the dispersion relation of any wave system that you're considering. So I'm saying that k minus delta k is the horizontal wave number, and the corresponding frequency is omega minus delta omega. And I'm considering its superposition with another wave whose wave number is slightly different. So I'm writing it as some mean value plus delta k. And the corresponding frequency is omega plus delta omega. Of course, what exactly omega plus delta omega is going to be given by the dispersion relation. You have to evaluate the dispersion relation, which is omega as a function of k. You have to evaluate it at k minus delta k to get the omega minus delta omega. And you have to evaluate it at k plus delta k to get the omega plus delta omega. But what's interesting is you can consider these close by plane waves, sum up the two, and you can write it in this form, where the first term is cos kx minus omega t. So that looks like a plane wave now that we wrote down earlier, a single plane wave. But now the amplitude of this plane wave, instead of given by a constant a above, now the amplitude is going to be given by cos of delta k into x minus delta omega into t. So in that sense, what we are considering here is like a plane wave whose amplitude is slowly varying with space and time. Why am I saying slowly? Because the wave number now for this amplitude part of the solution is delta k, and the frequency is delta omega. Delta k and delta omega being small, this corresponds to a large wavelength in x and a large time period in time. So if you plot this wave field, let's say at a fixed time, if you plot it as a function of x, you would first plot a typical plane wave or a sinusoidal wave whose wave number is given by k, or the wavelength is given by 2 pi by k. But then we've just argued that the amplitude is not constant. So if the amplitude was constant, this would be constant amplitude sinusoidal waves. And so you will put now an amplitude variation, which itself is a cosine function, but its wavelength is correspondingly 2 pi divided by delta k. So now I've drawn a wave field in space at a fixed time where the distance between these individual peaks is 2 pi over k, and but the envelope itself is now a cosine function with a larger wavelength. So the wavelength between the peaks of the envelope is going to be 2 pi divided by delta k. So the interpretation of the group velocity is that this peak associated with this envelope will move with the group velocity, and that's given by delta omega by delta k, as is evident in this expression. Okay, so if you want to move or stay on these individual peaks, and the amplitude associated with that peak may be continuously changing, you move with omega by k, which is the phase velocity. But if you're interested in remaining on top of an envelope, which is when you will actually stay in the energy intense region, because wherever the amplitudes are large is where the wave energy is maximum. So if you want to continue remaining on active energy wise active regions, then you are better off moving with the envelope or the group velocity, which is given by delta omega by delta k, which in the limit of small delta k is just given as written as dou omega by dou k, and 2D extension of it is what I wrote down in my derivation, where I said there is an x component of the group velocity given by dou omega by dou kx, and a z component given by dou omega by dou kz. So I will. I think Anubhav already showed this movie yesterday. So, but just for the continuity's sake, I will really quickly show you. This is probably the same movie. So what you are seeing here is these two individual plane waves shown on the top in red and blue. Okay, so the red and blue have slightly different phase velocities. So remaining on top of an individual wave, if only that plane wave was present, the phase velocity will have to be different. The red one moving with omega 1 by k1, and the blue dot here at the top moving with omega naught by k naught. But then when you sum up the two, what you see is that if you want to, and let's say omega 1 and omega naught are close to each other. Yeah.
We cannot see the videos.
Thank you. Thanks, Ramana, for reminding. I think I am not shared the entire screen. Let me share my entire screen. Thank you, Ramana. I stop sharing and I go share screen. Is it not possible to share the entire screen?
Yes, sir, it is possible.
Yeah, sure. Okay. Sorry about that. So let me just play that movie. What you're seeing on top are the two individual plane waves, one at wave number k1 and frequency omega 1, and the other at wave number k0 and frequency omega 0. If they were present individually, what you will see is shown on the top two panels. Okay, constant amplitude oscillations, and the red and the blue dots are moving with their respective phase velocities. And I think Anubhav pointed this out. If it's only an individual plane wave that is present in the system, there is no sense for you. You wouldn't see the evidence of a group velocity simply because energy is present everywhere in space. Right? But when you now combine these two waves with, let's say, K1 and K0 being close to each other, like I described in the previous slide, you're going to see. So what you have here is the wave field plotted as a function of space at different times as an animation. So if you want to remain at constant phase, that's exactly what the green dot is trying to do. And that would be an average omega by k that's associated between these two close by plane waves that you're considering. Right? So let's say the mean omega by k. But the omega 1 by k1 and omega 0 by k0 themselves are different from each other, which is what makes the system dispersive. But then if you want to remain on top of the envelope, which is where the wave energy is, then you should be moving along the purple dot. If you see, the purple dot is always in a region where the wave activity is strong. And that has to be done with a velocity given by the group velocity. So the magenta dot, or the purple, I called it purple, will have to be moving with the delta omega by delta k. Okay, so the equivalent of that is what we saw for the internal wave in the derivation, and you will see that in the upcoming slide. Ramana, can you confirm that you can see the slide?
Yes, sir. Yes.
Okay, thank you. Yes. So we derived the dispersion relation as given by omega square by n square equals sine square theta. And I gave this interpretation of theta being the angle that the wave vector makes with the z-axis. Okay. So now let's think of a scenario in which the background density gradient is fixed. So let's say n is fixed, and let's say the frequency of the internal waves is also fixed, because often in a real life setting you have some forcing mechanism that contains a frequency in it. And so the internal wave frequency, assuming that the generation mechanism is linear, we will say that the frequency of the internal waves that are generated is the same as the frequency present in the forcing. So in that sense, let's say the frequency is also fixed. So if both the frequency of the internal waves and the background density gradient are fixed, one wonders what the dispersion relation tells us. Dispersion relation will essentially give you what are the possible values of theta. So for a given omega comma n, there are 4 possible solutions for theta. These are just moving in the 4 different quadrants so that the value of sine square theta is conserved, right? Because omega n only fixes the value of sine square theta. So there are 4 different branches. And I have indicated the wave vector associated with the 4 different solutions that are possible with respect to theta, right? In each of them, you should see that theta is the axis. That is what is the case in the left top. And then the top right, again, the wave vector is inclined downwards, but the angle it makes with the z-axis is theta. Now, of course, the orientation is different for these 2 solutions. Similarly, you can also have these wave vectors where, again, theta continues to represent the angle that the wave vector makes with the vertical. One can also see what the corresponding group velocity for each of these solutions is. One thing we know already is that the group velocity is perpendicular to the phase velocity, which is what is indicated with the red arrow in each of these solutions. And you should also note, if you go into the details of what we derived for the group and the phase velocities, you should be able to show that if the wave vector has a positive z component, the corresponding group velocity will have a negative z component. So that eliminates the other possibility for the group velocity being orthogonal to k, because the other possibility, which is 180 degrees opposite of what is indicated here, will also have a positive z component. But you can go into the expressions for the phase and group velocities to see that the vertical components of the wave vector and the group velocities are opposite in sign. Okay. So what would this mean? As a summary, a plane wave which has a single wave number, you can write down now the plane wave as having a horizontal wave number k. Now the vertical wave number, instead of writing it as a kz, I'm writing it as k times cot theta. So theta referring to the wave vector orientation, and the frequency omega. But now the theta and the omega are related by this expression omega square equals n square sine square theta. What does a plane wave look like? This is just a MATLAB plot of what a plane wave would look like. Lines of constant phase will be as indicated. So this is one of the 4 branches. One of the 4 branches such that the wave vector is in the first quadrant. So that is inclined along the direction that is indicated as phase here, right? So lines of constant phase will all be along these lines of constant red or blue. And the wave vector itself, will go from one phase to another. That's indicated by the phase direction. The corresponding group velocity for this plane internal waves is orthogonal. And as I said earlier, phase velocity here has a positive z component. So the group velocity has to have a negative z component. So I'm choosing this branch, which is orthogonal to the phase velocity. And it turns out, because it's orthogonal, now a new interpretation for theta emerges, which is the angle that the group velocity makes with the horizontal. So theta can either be interpreted as the angle that the phase velocity or the wave vector makes with the z-axis, or the angle that the group velocity or the energy propagation direction makes with the horizontal x-axis. And one can also think about this, Anubhav did this for surface gravity waves. one can think about what the actual fluid particle motion is like. So you can write down dxp by dt equals u and dzp by dt equals w, where xp and zp are positions of the fluid particle. And for this plane internal wave, one can show that the fluid particles are just oscillating back and forth. In this plane wave, there is no Stokes drift, so these will be just oscillating back and forth along these lines of constant phase with zero net displacement. So as is common with all wave systems, so there is energy propagation associated with these waves. So if you input or impart energy in some spatial location, internal waves are capable of carrying that energy to far away distances, and those are carried along the group velocity vectors. But individual fluid particles themselves are just oscillating back and forth around a mean location. And the direction of this oscillation of these fluid particles is along the group velocity direction for these plane internal waves. So as a summary, I've just written that dispersion relation, interestingly, does not fix the magnitude of the wave vector. It only fixes the orientation of the wave vector. And yeah, so another interesting point that I forgot to mention is that now wave propagation is possible only if the internal wave frequency is some value between 0 and the Brunt-Weissala frequency, capital N. So the strength of the background density gradient fixes what are the allowable propagation frequencies for internal waves. And if you're considering small values of omega, the corresponding theta is 0. So then small frequency internal waves are very shallow internal waves. Shallow in the sense that the group velocity or the energy propagation direction will be very shallow with respect to the horizontal. They are almost horizontal. In the limit of 0 frequency, theta will be 0. So you'll have horizontal energy propagation, purely horizontal. And if omega is close to the Brunt-Weissala frequency, then the corresponding theta is pi by 2. So you are going to talk about the energy propagation direction being almost vertical. Okay, and of course, yeah, it's almost vertical is fixed. Whether it's upward or downward depends on causality, or in other words, it depends on the specific kind of forcing we have that will determine whether you will generate both the upward and the downward propagating internal waves, or maybe only one of the 4 solutions of theta will be picked up. And that's what I'm going to focus on in the next half an hour or so. Let me just check what time it is. So we have a good half an hour left. All right. Are there any questions? So there are no questions. Let's think of realizing this internal wave dispersion relation in a simple lab experiment. Okay, this picture was obtained by Mowbray and Rarity in 1967. So what they did was to fill a linear density profile or a uniform stratification. I will use these two terms interchangeably in a tank using salinity. Salinity is much easier to handle in a lab experiment. You will hear more about it from Silva when he talks about experimental studies. Okay, and in this experiment, what they did was to take a cylinder at the center of the picture. Okay, so there is this vertical suspension rod. We would let's assume that its effect is very minimal. And at the center, you have a circle, which is a cylinder, and that spans the entire width of the tank. And the width of the tank is in the direction that is coming out of the plane that we are looking at. Okay, so is that clear? That's the scenario. So you have the suspension rod holding a cylinder. So it's circular in cross section in the plane that we are looking at, and it extends the entire width of the tank in a direction perpendicular to this plane. And what these authors did was to simply oscillate this cylinder in the vertical direction with some frequency omega. That's a frequency that you prescribe. Okay, so you know the intensity of the density gradient that you have filled up, which means the value of the Brunt-Weissala frequency or capital N is fixed. Dispersion relation tells us that any frequency that's between 0 and the value of N should result in internal wave propagation. And we know that as the frequency is increased from 0 towards capital N, the direction of energy propagation or should go from being very shallow to very steep or vertical. And in this picture, so there is also a movie that I have. I will play that in a moment. In this picture, what you're seeing, the density gradients are being measured through this shadow graph technique, which is a very popular technique in compressible fluid flows. It turns out such techniques that take advantage of the fact that density gradients result in changes in refractive index. So that is getting picked up in this shadow graph imaging. Okay, and the purpose of these experiments were not to really quantify the value of the density gradients itself, but to visualize what the density gradient field looks like. Okay, and is it along expected lines? Yeah, the frequency omega is being prescribed. As soon as omega is prescribed, the dispersion relation tells us that 4 different values of theta are possible. And in this kind of a forcing, there is no reason why any of those 4 different thetas should be suppressed. So you do see 4 different arms of internal waves that emerge. Okay, so these 4 different, all of them correspond to the same angle that they make with the, let's say, the vertical axis. And they're all corresponding to the angle theta that the wave vector makes with the vertical given by the dispersion relation. So this, so at least that symmetry is observed. This is sometimes referred to as the Saint Andrews cross because of the similarity of the pattern with cross. Okay, so let me play the movie that I have. Ramana, can you please confirm that you're able to see the movie?
Yes, sir.
Thank you. Okay, so in this experiment, initially there is quiescent fluid, no density gradient perturbations. So this is the cylinder at the center, and yeah, you are holding it with a suspension rod that is as thin as it was possible to make, so that there is no influence of this thin rod itself. And you see in the experiment that is just being oscillated up and down vertically. But what sets the orientation of these internal waves is, we already know from the dispersion relation, is only the frequency of internal waves, which if it's in the linear regime is the same as the frequency with which the cylinder is being oscillated. Okay, in which direction is the energy propagating in this experiment? So you are inputting energy at the cylinder location, and you see that energy is radiating away from the cylinder. So in each of these arms, radiating out from the cylinder is the direction of the energy propagation for each of these 4 arms. And as expected, you do see, so for example, in this arm in the first quadrant, energy is propagating radially outward from the cylinder, but the phase itself, which you can track by keeping track of, let's say, one of these white lines, the phase itself is propagating orthogonal to the energy propagation, and its vertical component is negative because the energy propagation's vertical component is positive. So that in that sense, what you are seeing here is consistent with what we have deciphered from the dispersion relation, and all the 4 different arms are allowed. Was there a question? Was someone trying to ask a question in between? All right. So let me go back to my presentation.
Hello?
Yeah.
Sir, there are some questions in the chat box.
Okay. So what is it? I'll stop sharing. Go to the... yes, is this shadowgraphy? Yes, absolutely. This is just shadowgraphy, which picks up regions where density gradients perturbations are present. That's from Aritra. And then Suraj says, what are those irregularities near the cylinder? Okay, thanks for asking us that question. Let me share my screen again. So there are 2 aspects here. One is that the experiment starts off by the cylinder being stationary, and then you suddenly start oscillating at a frequency omega. So there are going to be that the initial time till the cylinder oscillations reach steady state, there are going to be transients that contain all ranges of frequencies, right? And we know as the frequencies range from 0 to n, the energy propagation direction goes from being horizontal to being vertical. So you will see an entire fan of internal waves generated both at the beginning, and if you noticed in the movie, even towards the end, there are the same transients because the cylinder is abruptly stopped. And so you have a range of frequencies excited because of that cylinder motion being brought to stop abruptly, and you will see an entire range of fan of waves that are generated. That is one. Two, in the near vicinity of the cylinder, things are a little more complicated than just being described by the inviscid plane waves that I have been talking about so far. Okay, particularly viscous effects are important in the vicinity of the cylinder. Because of after all, you want the cylinder motion to be communicated to the fluid, and in that process that happens via viscous mechanisms. So viscous and boundary layer effects are non-negligible in the vicinity of the cylinder. So there are papers. I can think of a couple of papers by Bruno Voisin and other authors that do talk about the wave field both in the vicinity of the cylinder. But what I wanted to focus on here is what you see sufficiently far from the cylinder, where at least the wave field has become clean and it seems to contain only the frequency omega that you put inside the forcing. But still, what we are seeing here are different from the plane waves that I spoke about, because for the plane waves, if you remember the image that I showed, that spans the entire spatial domain from -infinity to +infinity. But what you see here are essentially structures that seem to be finite in spatial extent. For example, these lines of constant phase are not going to extend to everywhere in the domain, right? And there was already a clue present in the dispersion relation, because we know that the frequency only fixes the wave vector orientation. And we don't know a priori which specific wave vector magnitude or the wave numbers are going to be actually excited. As long as the wave vector has the correct orientation, any wave number magnitude can be excited. And so it turns out in this problem, the specific wave number that is excited, it's not one, there are several wave numbers that are excited. And that's a function of the size or the wave spatial scales present in the forcing itself. Here you can think of the size of the cylinder, right, as essentially representative of the kind of wave numbers that would be excited. And so what we are seeing here as the wave field is not a pure plane wave that I discussed. It's a combination of plane waves or several wave numbers. Each of those wave numbers has a wave vector whose orientation is the same angle theta, because that's fixed by the frequency. But somehow a range of wave numbers have been excited. And that's exactly what I want to highlight here. This is what you see in a laboratory experiment, and this is often the case in the ocean also. What you observe are not nice plane waves that go from -infinity to infinity, but you see internal wave beams, which can be thought of as a combination of plane waves. So what I've indicated here in the expression at the top is a plane wave, so a constant amplitude psi naught. This here notation refers to the real part, and a horizontal wave number k. The vertical wave number now related, given by the dispersion relation. So, or is related, vertical wave number is related via the orientation theta and the frequency omega. And we know that the dispersion relation gives you a relation between theta and omega, but it allows for any k to exist. So which k actually gets excited depends on what is the kind of forcing that you put in. Okay, so I am showing here on the left is a plane wave. So this will be a single wave vector and only one branch of the 4 different solutions. So this is all downward propagating energy and phase velocity or the wave vector being orthogonal to that downward propagating energy. But now if you choose to sum up several such wave numbers, all of which correspond to the same theta, right? But I am saying that a range of horizontal wave numbers k are allowed. So now the amplitude itself is a function of k, and I'm going to sum them up through this integral. And one can think that, okay, this spectrum or the spectrum of wave numbers that you excite is, let's say, still peaked around a central value k naught. K naught, let's say, is fixed by the size of the cylinder that was oscillating. But then it does not excite only the k naught, but a range of wave numbers around k naught. So I'm assuming a Gaussian spectrum here. For the distribution, and I'm summing them all up. Each of those k's has a corresponding vertical wave number, which is given by k cot theta, and theta we know is already fixed by the frequency omega and the Brunt-Weissela frequency n. So finally the spatial picture that you will see will now be like a finite width internal wave beam. Here if you see, Yeah, so you're still seeing a wavelength, and this wavelength is kind of related to 2 pi over k naught, or the horizontal wavelength here is 2 pi by k naught. But then you also see that the amplitude is decreasing as you go away from the central region. This is reminiscent of what we saw as one of the arms from the cylinder. And this is in contrast to a plane wave where the amplitude is the same as you just keep going from one phase to another continuously all the way from minus infinity to infinity. But on what you see on the right is what is representative of what you see in any lab experiment or in the ocean or the atmosphere, because you always have some finite size associated with the forcing mechanism. And so you have a combination of wave numbers. Again, I have shown only one arm of the 4 different arms of the St. Andrews cross that I have shown here.
Sir, I have a doubt here. So the experiment you have shown earlier, so in the surface, you will be seeing the plane wave like this, and the internal in the layer between two density layers only you can see the right hand side picture. Is it like that? The experiment you showed, no? The cylinder going up. So at the surface, you will be seeing the plane waves.
So no, so this is so what you are seeing here. This is the x-axis and this is the z-axis. So what the picture that you are seeing here is in the internal bulk of the fluid. So it will have some signature on the water surface as well. But that signature is not what we are picking up now. That itself is a separate interesting question as to what is the surface signatures of these internal waves. But what we are seeing here is the internal bulk of the fluid. So this is like you have gone to subsurface depths in the ocean.
Okay, okay, I got it.
You will see in the ocean. And I have a picture or a movie from in the next lecture where I will say that what we are visualizing here is essentially that there are several interfaces, constant density lines that are present in our system, because we have this continuous stratification. Yeah, so you can imagine that there are these horizontal lines which are lines of constant density, and there are infinitely many of them. So this is the equivalent of the water-air interface that Anubhav considered yesterday. But now you have these interfaces. You don't have abrupt jump in density. These are all continuous variations in density, but we have infinitely many such interfaces. And each of those interfaces can support waves, and they also have to be connected to one another because they are all present one below another. So connection of all these waves that you see in individual interfaces is what forms the internal wave. So the word internal in the internal wave refers to the fact that this happens in the internal region of the fluid and not just a surface phenomenon.
Okay. Okay.
Did I answer your question, Simi? Yeah. Okay. So what we are seeing here is what happens in the bulk or the internal region. So, and the color indicates the density gradient perturbations. The velocity perturbations also will show a similar picture. So initially you had the density gradient that was purely vertical, and that was a function of z only. But then in the presence of these waves, a density gradient will now have this very interesting spatial structure.
Hello,
Okay.
I'm Mani. Hello.
Yeah, is there a question?
Yeah, so I was wondering, like, what sets the sigma in this omega naught k?
Well, for this MATLAB plot, I just took a random sigma. What would set the sigma is again the structure, the spatial structure, or the spatial length scales that are present in the forcing. So one has to, so for the cylinder problem, we will have to go into the details of representing the cylinder as a distribution of sources and see what sigmas we get. So I can only say that it's a function of both the dominant spatial scale and the distribution of spatial scales that are present in the forcing. Okay, and I will touch upon this topic again when we talk about ocean floor topography generating internal waves in the next lecture.
Sure. Yeah. Thank you.
Okay. Yeah. So now another extension. So we saw that plane waves is not what you observe in reality. It's a combination of wave numbers that forms a finite width wave beam. Another interesting extension or constraint to keep in mind is that we never have infinite spatial extent medium, right? Especially in the vertical along the z direction, you are always going to have boundaries, be it the atmosphere or the ocean. So you are going to have finite depth regions, and it's the same in the laboratory experiment. One can think of even having horizontal extents that are much larger than the wavelengths in these internal waves. But in the vertical direction, you're always going to be constrained. This is just given by the fluid depth that you fill in your tank, right? And the introduction of these boundaries at z, let's say in this picture at z equals 0 and z equals h, breaks the homogeneity in z. So this is somewhat like someone asked, if n is a function of z, what will you do? Now I am saying n is still a constant, but I'm saying there are boundaries, horizontal boundaries that you have introduced, and some boundary conditions are to be satisfied. So we cannot just have any plane wave that is possible. Only those plane waves that can satisfy these boundary conditions. These boundary conditions are just no normal flow at the bottom and the top. So assume that it's a rigid lid at the top of this water surface and the tank bottom at the bottom, and you need the vertical velocity to be equal to 0. So all those plane waves that I considered in the previous slide, only a few of them are actually going to satisfy. Only some of them, actually none of those individual plane waves will satisfy those boundary conditions. You will have to figure out a way of combining those plane waves intelligently to satisfy this boundary condition. Or mathematically, what one can do is not assume the exponential variation along z. Instead, keep it as some arbitrary function of z. Okay, so which is what you would do. You would take the internal wave equation. Here, I was sorry for switching the notation. This is now for the vertical velocity. Turns out both the stream function and the vertical velocity are governed by the same equation. So now in the vertical direction, I will not say e power I kz into z, which is like a single wave number kz. Instead, I will just leave it as capital W of z and allow the equation to tell me what capital W of z is. In the horizontal, it's still infinite in extent. So I'm allowing for an exponential or a wave-like behavior along x. So once you do this, substitute this waveform in the governing equation, you are now going to get a governing ordinary differential equation for this vertical mode shape W of z. Okay, so this still contains the information on dispersion relation. Earlier, we substituted e power I kz into z, and we just got a relation between kx, kz, and omega, and that was the dispersion relation. Now we are getting a governing ordinary differential equation for the vertical profile capital W of z. Okay, and but this is a sufficiently simple linear ODE that one can solve. The different solutions are sinusoids for W, or in terms of the horizontal velocity, they are cosines. And there are only specific wave numbers that are allowed so that this boundary conditions can be satisfied. Because the general solution is given by sine the wave number fixed by this coefficient z, but then only a discrete set of those wave numbers can actually satisfy these boundary conditions. And so you're going to have finally the solutions being given by these discrete vertical wave numbers that is indicated by the mode number n, and the relation between the horizontal wave number kx and the vertical mode number n. Again, that relation here is fixed by the dispersion relation. Okay, so finally, any general wave field, instead of being written as a summation over plane waves, you are now going to write it as a summation over these modes. And the relative sign between kx and omega is going to tell you whether these modes are propagating from left to right or if they are propagating from right to left. Is that okay? So what I've written down at the bottom here is, now that in the presence of these horizontal boundaries, general linear wave field is to be thought of as a combination of these different modes, starting from mode 1 to infinity in general. Again, related to the previous question, which modes are you actually going to see? That depends on the forcing mechanism. What are the length scales present in the forcing? That's going to determine which modes actually get excited. But in general, if you don't have much clue about it and you're going to allow for any modes to be present in the system, you write down a linear combination of all possible modes. And these mode numbers, these are now, if you want to think of n pi by h as a vertical wave number, then only these discrete wave numbers are allowed so that the boundary conditions can be satisfied. This is exactly like if you have a vibrating string, but then if you want to have a boundary condition that the vibrating string has to satisfy, then the number of wave numbers become discrete. You cannot allow a continuous range of wave numbers to exist. So similarly, the number of possible horizontal wave numbers are now discretized because of this boundary conditions. Let me check the time. Are there any questions? Ramana, can you please confirm if there are any questions on the chat box?
No, sir.
Okay, so it's already 3:30. What I suggest is that I will stop here. I have also another meeting to go to, and I will continue with my lecture on internal waves in the ocean. But then what I will do is start from this point, laboratory modeling of internal waves. And I will try to, so what I had planned for the rest of this lecture is to show how you can excite specific forms of these internal waves in a laboratory experiment. Maybe it's not a bad thing that we have to stop here, because Silva in the afternoon, in the evening, will talk about experimental studies. So that would also give you some feel for how experiments are conducted in the general area of stratified flows. Then we would be able to appreciate some of these wave generator slides that I have prepared in the context of what Silva would tell us about. So I will spend the first half of my next lecture talking about generating these various internal waves in the lab. They are all essentially sophisticated extensions of the oscillating cylinder experiment. And the second half of the next lecture, I will spend on how internal waves are generated in the ocean and what are important problems in the ocean that people think about. Okay. So any further questions, please include in the chat box or send me an email. I will be happy to take them in the beginning of my next lecture. Thank you. Ramana, can you take care of stopping the streaming?
Yes, sir.